Okay, the last expression to type check in TFAE is function call E1, E2, E1, E2. So under this given type environment gamma, how do we check the type of function call E1, E2? We first check the type of the function part E1 under the given type environment. What do you expect as the type of this first sub-expression E1? Because it's a function call, we expect that the first sub-expression has an arrow type. And we don't know the types of its parameter type and return type. All we know is it's an arrow type. If it has a number type, we are in trouble, right? The type of E1 should be an arrow type with some parameter type and some return type. So we call them tau1 and tau2. And this type of this function part E1 could have the same type for the parameter and the return type, right? Meaning that we said that the type of E1 is tau1 arrow tau2. Here, tau1 and tau2 are arbitrary types, meaning that they could be the same, they could be different. We didn't say anything about their relation. And the second premise is under the same type environment gamma, when we type check the second sub-expression E2, its type should be tau1. Now there's a connection from the type of E2 to the type of the parameter type of this, the parameter type of the arrow type of E1, right? So when we type check the second sub-expression E2, we are going to have some type tau3. And all we are saying is that tau1 and tau3 should be the same. That's it, right? So these two premises and these three premises represent the same thing. Are you with me? Yeah. And then the type of the function call is going to be the type of the result of this function part, right? The type of this return type. So the type of the function call is going to be tau2. So we knew that. We learned that before. And how can we implement this in Scala? Type check takes an expression and a type environment. Type check takes the expression to type check and the type environment. Under this type environment, when the expression was function call E1, E2, FA, we are gonna type check F, we are gonna type check A, and the type of F should be an arrow type, and the type of A should be the parameter type of that arrow type. Then the type of the whole expression, whole function call is going to be the type of the return type. Ooh, how can you do that? We are going to type check the first sub-expression, which should be an arrow type, right? And we just name it fun T. We type check the second sub-expression, which should be the same type with the parameter type of fun T, right? But anyway, we just name it the type of the second sub-expression argt. So all in this, typing rule, font is tau1 arrow tau2 and rt is tau1. So font should be an arrow type and argt should be the first parameter type of that arrow type. How do we say that? Like this. Font should be an arrow type. This is what we said just now, right? Font should be an arrow type. If it's a number type, error saying, hey, you are applying the type of this second sub-expression to num-t. It doesn't make any sense. Font should be an arrow type instead of num-t. If it's an arrow type, it has parameter type and return type. What do we know? Yeah, one more time. Font T is now this arrow type from param to result. And we know that the type of E2 is argt. Argt and this param should be the same. Then the type of the whole expression is what? Result. So we say that if argt and param are the same, then the type of this whole function call expression is going to be result. Do you see this conditional pattern, right? We could just say that case arrow t and if this, that, else, no type. We could do that too. arrow t 하고 바로 그냥 화살표 한 다음에 if else로 또 똑같이 else일 경우에 no type throw 하게 할 수도 있어요. 근데 그렇게 안 했네. 그죠? Instead of doing that, we are using this conditional pattern. So when font t is an arrow t, but when its parameter type is different from argt, then we just match to this case instead of the first case. The first case matches only when font t is an arrow t with parameter type and return type, and that parameter type is same with argt, right? So this is the whole just single pattern. If so, the type of the function call expression is going to be result. Isn't it cool, right? Yeah, okay. So this is it for type checking this simple language called TFAE. TFAE. FAE with type. The minimal addition to FAE. FAE with type annotation. When we have function expression, we annotate type to this parameter. That's TFAE. Then, is it good enough? If TFAE is true and complete, then we could just stop here, but not really. In order to show the limitation of TFAE, we are going to see some feature. Do you remember in the midterm exam, just before the midterm exam, we had one lecture talking about growing languages. If you remember, yeah, the title was Growing a Language, and that lecture was a brand new one, meaning that we didn't have that lecture until last semester. 중간고사 직전에 했던 그 강의는 이번 학기에 처음 들어간 거예요. 지금까지 한 번도 한 거 아니에요. Because this semester we have new kind of midterm exam, this take-home open book midterm exam that we never tried before. 이번 중간고사는 우리도 처음 해보는 거거든요. 그래서 해봤는데 괜찮았는데 앞으로는 안 할 것 같아요. It was really good and it was fun actually to us, and some students really liked that and they gave us positive inputs, but it was too much, a lot of work for TAs, for grading. So it was a good try. We learned a lot and we are not going to do that again. Yeah, that was kind of a trial thanks to or due to this COVID-19 situation. So in order to do that, in order to have such a new kind of midterm exam, we added that lecture Growing a Language, and I gave you 2 examples of adding a feature to an existing language. So 여러분 중간고사 그나마 그래도 좀 볼 수 있게 하려고 새로운 렉처 집어넣은 거였어요. 중간고사 완전 새로운 거니까 이런 식으로 하는 거예요 해서 제가 샘플 보여줬었죠. Adding pairs, if you remember, right? And this time, back then, we added those features to FAE. FAE, very close to lambda calculus, which is Turing complete. But this time, TFAE. TFAE is not Turing complete. 람다 캘큘러스는 랭귀지 컨스트럭터가 3개밖에 없는데도 Turing complete한데 TFA는 Turing complete하지 않아요. Meaning that there are some example code that TFAE cannot represent. Meaning that even though it's a perfectly good code, TFAE is going to reject that. Remember? 기억나세요? Remember? When there is a set of programs there could be a subset of that with bad programs. And identifying that set exactly and reject them before running is not possible. Impossible. Right? It's undecidable. The problem to identify the set exactly is an undecidable problem. So all we can do is just to say that, hey, all of them is really good. And missing all of them is really bad and missing those bad parts. Or saying that, hey, all of this is bad, rejecting good examples, right? What we are doing right now with TFAE is like having really big set and reject all of them, meaning these pairs are not possible to type check in TFAE. TFAE is going to reject some code that are perfectly good, like these things. And our purpose today is to grow the language so that we can accept, we can accept more example like this. They're pretty good, and we are going to accept it by reducing the set of bad programs. That's how we grow the language. Let's see, before diving into the new language, let's see some examples and try to understand the limitation of TFAE. Here is an example. Let's see. We have 1, 2, 3 names. What are they? The first one is a pair, trying to make a pair. First, takes a pair and produces the first component of the pair. Second, takes a pair and produces the second component of the pair. How can you make a pair? It's a function that takes two numbers and produces a pair. What? If you don't get it, let's see how that can be used and come back to how we can construct a pair. First, again, takes a pair, produces the first component of the pair. Second, takes a pair and produces the second component of the pair. This time, pairs have only numbers. So more precisely, number pairs. Right? So a pair is a function. That's our encoding of a pair. Right? And if you take a pair whose type is an arrow type from num to num, and then when we call first on a pair, we are gonna say, hey, I'm gonna apply that pair function with 0. Okay. Second, meaning that we are going to apply the pair with 1, meaning that this pair is a function which takes a number and then returns either first component or the second component. Are you with me? Yeah. Do you have a guess how we can make a pair? Let's see. A pair is a function which takes two numbers and then produces another function. Ooh. This pair takes the first component, the second component, and then returns this function, which takes a number, and if the number is 0, then returns x. Otherwise, y. Ooh, isn't it cool? Do you see the secret? Do you see how it works? Pair takes the first number and the second number and keeps them in this closure V, right? And it asks for the index. Hey, do you want the first one or second one? If the input is 0, then returns the first component. Otherwise, the second component. That's our pair as a function value. Let's see how we can use it. When we construct a pair with 1 and 2, then we call this function with what? 1 and 2, right? Actually 1 to x, 2 to y, 1 and 2. Then this open pair 1 to close, meaning a closure V, which waits for some number, and if the number is 0, then return 1, otherwise 2, right? And let's call second function using this pair. Okay, second function takes a pair, which is this one, and then it calls the pair with 1, calls this pair with 1, calls this pair with 1. S is 1, so the return y, which is 2. Are you with me? Yeah? It's not that difficult. I took too much time explaining this example. You'd better do that by yourself. Let's look at the second example, which is very similar but slightly different. This time, a pair takes 2 booleans and then returns a function. The first component, the second component, and again a function that takes an index, and depending on the index, return the first boolean or the second boolean. Then the first function takes a pair. This time a pair is a function from number to boolean, meaning again this time it's a boolean pair. Okay, so both first and second, it takes a pair, produces a boolean. If the index is 0, returns the first one. If the index is 1, returns the second one. And this example has a typo. It's gonna be what? Say true and false, let's say. Then, let's construct a pair. How do you construct a pair? Takes 2 booleans, true and false, right? True and false. And then, like this, what is it gonna be? It's like, get the index, which is a number. If the number is 0, right? If the number is 0, return x, which is x true, otherwise false, right? Yeah, it's like that. Then, call the second function using this pair. Then, second says, hey, takes a pair, this purple one, and then returns boolean. Okay, then it calls p with 1. It's not 0, so it's going to be false. Are you with me? Okay, then let's try the third example. How does it work? A pair this time takes a number and a boolean and produces a pair. The first and the second, we are in trouble. We get stuck. Why? What's wrong here? 뭔가가 이상한데 뭐가 이상하지? 뭐가 이상할까요? First and second, it takes a pair, which takes a number. Depending on the number, it returns either number or boolean. Wow. The first example, that number pairs. The second example was boolean pairs. And the third example is what? Number and boolean pair? Wow. It doesn't work. It's not working. Because depending on the first or second, depending on the index, number pair returns a number. Boolean pair returns a boolean. Number boolean pair returns what? We don't know. Depending on the index, we need to return either number or boolean. They have different types. We are in trouble. And we have another typo here. I'm going to fix that later. Okay? Wow. What can we do about it? Remember, when we have an if expression, if 0, E1, E2, E3, we said that, E1 is 0, then we are going to evaluate E2. If E1 is non-zero, we are going to evaluate E3. What's going to be the type of E2 and E3? We discussed that there could be several options. Either what? They should be the same type, or union type, or subtype. But in this semester, until the end of this semester, we are gonna enforce that those branches should have the same type. Those branches, first or second, they should have the same type. So we cannot do that. Then what can you do? Extend the language, right? There's no possible type for dot, dot, dot. Remember, this was the language before midterm exam. And we extended the language with pair. Constructing a pair, getting the first and the second component, and we learned its operational semantics, and we learned how to extend abstract syntax, and how to extend the value to have pair V, and how to implement the interpreter, how to construct a pair value, how to get the first component or the second component, right? Similarly, we'd like to extend FAE, actually TFAE, with a pair. This time, we have a pair expression, first component, second component, those expressions. And we extend the type, not only the value, but also the type, to have a pair value. So previously, we talked about the interpreter. Now, we are talking about types. What are their types? Yeah, there's nothing complex. That's the operational semantics, right? Under a given environment, when we have a pair expression, we evaluate the first component, we evaluate the second component, get those two values, and make a pair. Just like that. When we have a pair expression under the type environment, we are going to check the first component, we are going to check the second component, get their types, and make a pair type. Simple. How about getting the component? Getting the first component, getting the second component. Yeah, look at this operational semantics first, as usual. Under the given environment, getting the first component, meaning that when we interpret this expression, we should have a pair value. And we're getting the first component, we only get the first component. Just like that. When we have an expression with getting the first component, we need to type check the expression that should have the pair type. If it has number type, error. Arrow type, error. Pair type. And those pair, the first component and the second component, they do not need to have the same type. They can have the same type. They may have the same type, but they do not need to have the same type. So the type of the first component. So cool, right? And then second is just like that. Interpret it, yeah? Just like the operational semantics, interpreting that expression should produce a pair value, and we are gonna get the second value, the value of the second component. And type checking is just like that. When we have E.2 getting the second component of this pair, we need to type check that expression, get the pair type, right? And get the type of the second component. That's it. That's all we do. When we have some simple expression and that expression cannot represent really good idioms or really good feature like pairs, then we are gonna extend that. We are extending its concrete or abstract syntax. We are extending its abstract syntax. We are extending its type and value, and write down operational semantics and typing rules. That's how we grow a language. This is it for today's lecture, and this is the second picture of our fall foliage.